Okay, so chapter 9 was on solids and fluids. We talked about the four states of matter: solid, liquid, gas, and plasma. Plasma are pretty much the electromagnetically charged particles that are at large in the universe. And then in our environment on Earth, we mostly deal with liquids, solids, and gases. Your solids have definite shape and volume. Liquid has definite volume, but no definite shape. It takes the shape of whatever container it is in. And gas has neither a definite volume or shape. We also talked about elasticity, um, especially in chapter 6, I believe, when we talked about elastic collisions and inelastic collisions, where elastic, they pretty much, there's no deformation, so no change in shape. So they collide but bounce back to its initial form and shape. Types of matter. We talked about how only 5% of all matter is what we know of as normal matter in our universe. Most of it is either dark matter, which is 25%, and then dark energy, which is 70% of the matter in the universe. We talked about stress and strain. Stress is force per unit area, and strain is the measure and the amount of deformation. Um, Stress is just like another word for pressure. So stress is force over unit area. I was talking about elastic modulus and how materials having elastic modulus are pretty stiff and difficult to conform. We talk about Hooke's law, which we talked about it briefly earlier, but I told you we would see it again later in the semester. That's where the spring force is equal to the spring constant uh, times the change in, this is pretty much the stretch or compression of the spring. Let's see. We talked about the SI unit for stress, which is another word for pressure. All right, pressure is in pascals, and that is force over area, which is newtons over meters squared. So sometimes you'll see it in pascals, and sometimes you'll see it in newtons over meters squared. We talked about tensile strain. So that's a type of pressure. So force over area is equal to the proportionality constant called Young's modulus. Again, it varies from um, material to material. And then delta L is the change in length. So final length minus initial length divided by the original length. So the initial length is there. All right, so again, stress is another word for pressure, which is force over area, and that is in pascals. We talked about density as well. Density is denoted by the Greek letter rho, kind of looks like a P, but it's not a P. And it's the mass divided by the volume. So in SI units, that will be kilograms over meters cubed. We talked about different densities. The density of water is greater than the density of ice, air, and cooking oil. And that is why those um, substances that are less dense than water always float on top of water. All right, so if you've ever mixed cooking oil, they don't mix due to the different densities. And then the oil floats on top of the water because it has a lower density than the water. So more dense sinks, less dense floats. You will need to try to understand that. Okay, so variations of pressure with depth. All right, so when you have a fluid and it's resting in a container, all portions of the fluid must be in static equilibrium. All right, so at all points at the same depth, they will have the same pressure. All right, so if it's a different depth, then it will be a different pressure. All right, so for the variation of pressure with depth equation, its pressure is equal to the original pressure, which is the standard atmospheric pressure, 1.013 times 10 to the fifth pascals. This is a constant. If you're not going to memorize it, please make sure that it's on your formula sheet. So your original pressure plus the density times gravity times the height or depth of the substance in question. All right. Pascal's principle, that is a change in pressure applied to an enclosed fluid, is transmitted undiminished to every point of the fluid and to the walls of the container. Buoyancy forces and Archimedes principle. So sometimes when you have an object that is either partially or submerged in a fluid, you get an upward force, which is called the buoyancy force. All right, so buoyancy force is denoted by B, rho of the fluid, so that's the density of the fluid, times the volume, times the, this is the gravity. So that's the 9.8 meters per second squared. All right, surface tension, viscosity, and Reynolds number. Okay, now I do remember going over this. Okay, so your surface tension, that is the magnitude of the surface force, tension force. All right, and it's force over the length of the fluid. Also, we talked about Reynolds number and viscosity. Viscosity is the thickness of the fluid and how well it flows. So the viscosity is something that varies from substance to substance. So the viscosity of water would be different than the viscosity of honey because the thickness in honey is, slightly different than water. So it flows a bit slower. All right. Fluids in motion. We talked about the equation for the flow rate through a pipe, and that's going to be the cross-sectional area times the speed at two different points throughout that pipe, and they are equal to each other because of the equation of continuity here. So make sure that is on the formula sheet. Fluids in motion. So sum of the pressure, the kinetic energy per unit volume, and the potential energy per unit volume is the same at any 2 points along that streamline. This is the equation for that. So you have the pressure at 1 point plus your kinetic energy, which is 1/2 mass times velocity squared, which here they have the density instead of the mass. And then you have your potential energy, which is your mass times gravity times height, which here is going to be density times gravity times your height in the y direction. And then the same is equal on the other side for the second part of that point. And this is known as Bernoulli's equation. So this is fluids in motion, very similar to the work energy theorem. All right. Diffusion and osmosis. So in the diffusion process, we have molecules that move from a region of high concentration to low concentration. This is the equation for diffusion, which is called Fick's law. So the diffusion rate is equal to the mass of the substance over time. All right, so, and then another process is called osmosis. And if you've ever drinking bottled water before, this is what most of the filtration processes include to clean the water. So it's the diffusion of water across a selectively permeable membrane from high to low water concentration. All right. And then we have a couple more problems that we're going to do. So let me go ahead and get to the whiteboard as well. Put that here. Okay, so number one, find pressure when the force is 490 newtons and the area is 26 times 10 to the minus 4 meters squared. All right, so if I'm not mistaken, we should be caught up now on the slides. All right, so this is number one. All right, so pressure is equal to force divided by area. They gave us the force of 490 newtons. All right. So if you type 490 newtons divided by 26 times 10 to the minus 4 power meters squared, you will end up with 62 newtons over meters squared. And let me clean that up a bit. Newtons over meters squared. All right, let's see what number 2 says. Find the density when mass is 133 grams and the volume is 10 meters cubed. All right, so first of all, mass is in grams and the SI unit for mass is kilograms. So we will need to convert by moving the decimal places, decimal place 3 places to the left. And then we have the volume, and there's a little hint there that says use the SI units. All right, so mass SI units is in kilograms and not grams, so we will need to convert that before plugging it into the density equation. All right, so we're asked to find density. All right, density is the Greek letter rho. Looks like a P, but it's not a P. All right, density is mass divided by volume. All right, our mass was 133 grams. If we change that to kilograms, it'll be 0.133 kilograms. And then the volume was 10 meters cubed. 10 meters cubed. So 0.133 divided by 10, you would end up with 0.01 kilograms over meters cubed. All right, let's see what number 3 says. Find pressure when the original pressure is 1.013 times 10 to the 5th pascals. Density is 700 kilograms over meters cubed, and height is 0.3 meters. All right. So for this equation, we're going to use the pressure at depth equation. So that's going to be pressure is equal to the original pressure, which they gave us, plus the density times the effects of gravity times height. All right, and then from here we plug everything in. So this is the 1.013 times 10 to the 5th pascals plus our density, which they said was 700 kilograms over meters cubed times our gravity here, which is 9.8 meters per second squared, 9.8 meters per second squared, and then times the depth, which they told us was 0.3 meters. That's 0.3 meters. All right. Once you plug all of that into your calculator, you should end up with 103,358 pascals. All right. And then last but not least, number 4, using Archimedes' principle, solve for the volume if our buoyancy force is 100 newtons, density is 700 kilograms over meters cubed. All right, so let's go back to the whiteboard for number 4. Number 4. All right, so if you remember the buoyancy force, that was equal to the density of the fluid times the let's go back to the equation here. Density times volume times gravity. All right. Make sure you guys update your formula sheets and have that on there. All right, let's go back down to the problem. All right, and we're trying to solve for the volume. All right, so here the volume is the unknown. All right. Okay, so to solve for the volume, we need to get rid of the other two variables. So divide by density and gravity on both sides. What you do to one side, you got to do to the other. All right, these cancel out, and you'll end up with volume is equal to the buoyancy force divided by density times gravity. They told us the buoyancy force was 100 newtons. All right, they told us the density was 700 kilograms over meters cubed. And then we know gravity already, that is 9.8 meters per second squared. That's a 2 right there. All right, and once you plug all of that into your calculator, you should end up with 0.015 meters cubed.